or good evening to our participants from the workshop presenters at Innovate for Climate. My name is Alessia Falzarone, and I have the honor to moderate a discussion of the entrepreneurial breakthroughs taking place around the world, with particular focus on the production of green hydrogen. Now, the last couple of months, the international focus on green hydrogen and whether it could become a viable tool at scale in meeting the carbon neutrality needs and obviously the ambitions of many countries and sectors in the world has been amplified. In fact, a little over a month ago, the European Commission released the EU criteria on sustainable hydrogen activities, and clearly clearing the way for targeting deployment of the technology and opening the door for regional collaboration. Not to mention that the recent revision of the 2050 report by the International Energy Agency forecasts that staggering amount of green hydrogen needed for the world to reach net zero by 2050, approximately 306 million tons per year. We are bringing today the innovation and the policy support lenses to this dialogue at Innovate for Climate. And we have with us from Quebec, Canada, Dino Mihanovic, founder and CEO of startup innovator Cesar Energy. Cesar has been recognized in a variety of forums for its targeted approach to the integration of renewable hydrogen to power small-scale industrial processes and solve the problem of scale through modular design. Welcome, Dino, and thank you to Cesar Energy for hosting this discussion today. From Australia, it is my honor to introduce Professor Behdat Moqtaderi, Director of the Priority Research Center for Frontier Energy Technologies and Utilization at the University of Newcastle. Professor Moqtaderi is a leading voice in the Australian R&D community for renewable energy sources to achieve carbon neutrality, not to mention an internationally recognized innovator. Welcome to Innovate for Climate, Behdat. Such a late time for you.
Thank you.
We would not have a complete picture of the world's innovation pipeline if we didn't focus on the state of hydrogen production dialogue and the policy direction for China. And I'm honored to introduce Ms. Agnes Lee, manager in the China program at the Rocky Mountain Institute based in Beijing. Agnes will introduce us to the role of green hydrogen and the pace of new project development in China, with a specific example of the transportation sector for technology deployment. Welcome, Agnes. Now, a few housekeeping reminders for our audience. Please feel free to share your questions in the chat box during the discussion. We will have a Q&A session in the last 10-15 minutes of today's workshop, and we'll also answer all your questions at that point. Now, the podium goes to Canada with Dino and Cesar Energy. Dino, I'll now be sharing the background materials for our audience to follow the discussion. Thank you.
Great. Well, thank you for the introduction, Alessia. It's a pleasure to be part of this panel, and I think we have some great people in here to make for an interesting discussion and hopefully some great questions to follow through. So it really is a pleasure to come here and discuss the landscape for renewable hydrogen in Canada as a first thing, and then present to you people how maybe if you can just go back to the first slide, Alessia, for the moment, and so maybe once we have a picture of the larger landscape in Canada for cleaner hydrogen. I will sort of go through how we at Cesar Energy are fitting in this Canadian strategy for hydrogen and where we will try to bring value. So Cesar Energy, just quickly, is a startup, a spin-off company from university in Canada here, and we're looking to bring our technology to the market as soon as possible and have impact. So if you really look closer to the landscape for renewable hydrogen in Canada, it's really convenient for me to sort of address this, to present it, because quite recently Canada put together this really thorough Canadian hydrogen strategy, and really expanding on the goals in the short, mid, and long term for hydrogen production, utilization, and potentially even for storage and for a long-term energy usage. So really what the focus for hydrogen in Canada in the short term will really be to put the table on the future steps. So it will be about focusing on what's already out there in terms of applications. So mostly industry. If you think of hydrogen in iron making, steel making, in the chemical industry, in ammonia production. So that's one aspect. And the second one will really be about deploying hubs in specific regions and sectors. And I'll go through that a bit later on. But so it's really about putting on the table. While in the next 5 years after that, from 2025 to 2030, it will be around expanding the efforts from industrial application to other sectors and regions. So really, it's about, okay, we were able to develop these competences and these technologies, mature them, and we can look into newer applications. And then after these first 10 years of really putting the table for applications and the technology itself that will produce and exploit hydrogen, the remainder up until the net zero CO2 objective of the country in 2050 will be about growth. So really focus on increasing hydrogen supply and distribution infrastructure. And by that point, the idea is that there will be a more defined division between battery and fuel cell use. So it will really lead the way as well. So if we look at current hydrogen picture, it's about 3 megatons per year, and a conservative scenario in the Canadian hydrogen strategy will raise this to 8.3 megatons per year. An optimistic one goes to 20 megatons of hydrogen per year. So there really is a question of how are we going to use this hydrogen exactly, and how are we going to produce it? So there's really a question of push and pull, if you like, on that side. And the country is really looking into helping this with funds on both spectrums, on both ends of the spectrum. So there is federal investment of $1.5 billion in low carbon and zero emissions fuels, including hydrogen, of course. There's also a lot of funding, $150 million over the next 3 years in vehicle charging and refueling stations. So it's really from utilization and production perspectives. And there's some estimates that go from $5 to $7 billion of total that could be invested by the end of the 2020s. And so quite recently, if we look at the picture, well, at the bottom right, you can see a map of Canada. And I'm showing here very recent projects in renewable hydrogen that span from production to application and also research. So how are we going to make it? How are we going to use it? And what's up next? And so you can go to the next slide, Alessia. So really what this shows is that there is a high level of regionality in the hydrogen use in Canada. So this variety of projects I was showing is really in phase with the country's extremely diverse geography. What I mean is that the solutions that are pushed more aggressively tend to depend greatly on regional factors. So in Quebec, where 99% of the electricity is produced with hydro, so it's clean, there is great focus on electrolyzers. On the West Coast in Alberta, where major hydrogen users in highly functional gas grids are already present, it is rather hydrogen storage at scale that is pursued. So while keeping the end goal of a decarbonized economy in mind, Canada's strategy also aims to leverage the country's resources as much as possible to allow a smooth economic transition. And I think the way to do this transition is really to work on versatile solutions that in the long term can allow net zero CO2 production of hydrogen, but I can also reduce CO2 emissions significantly in the short term without necessarily being net zero right away. And one of those solutions is what we're doing at Caesar Energy, which is electrifying the reforming process. You can switch, Alessia. And so the reforming process, there is a little schematic on the top right, if you look at it, is really what's at the source of the not so liked gray hydrogen that most people have heard of. And so basically uses natural gas with water, uses heat from combustion to allow the chemical reaction that separates the hydrogen from the carbon and producing hydrogen alongside CO2. So what is not converted in the reactor goes back to the burner, and really the byproducts are mostly hydrogen and CO2. So why is this still interesting? Well, One thing is that reforming requires 4 times less energy per kilogram of hydrogen than electrolysis. So in the long term, or in the short term at least, this can allow a smoother transition to renewables. So if we look at IEA's sustainable development scenario for chemicals, well, they put a lot of emphasis on the need for less energy intensive processes for chemicals production. And so if you're able to electrify this, so instead of using energy from combustion, rather electrify chemistry, it can have a lot of positive impact in terms of decarbonization. Another thing is biogenic feedstock is greatly underused right now. The global potential is about 3,000 terawatt hours worth of biogas from livestock manure alone. So some rough calculations on my side, this is enough feedstock for reforming to produce 100 megatons per year of hydrogen. So this is more than the quantity of hydrogen that is used right now. And this is only from livestock, right? No landfill gas considered. And so then you have a completely green hydrogen. And another thing is electrification, fully leverages the chemical value of the feedstock. So rather than burning it, well, you can use electricity to produce heat, and you can really use all of the chemical value in there and produce hydrogen with it. Finally, along hydrogen, we can also see CO2 and the carbon in biogenic feedstock as a source of added value products. So the carbon can be stored in a variety of essential products in the current economy. So we're talking about paints, adhesives, solvents, fabric. It's really products that for a little while still will rely on carbon as a central piece. And so that's really why at Caesar we're looking at electrifying the reforming process. So you can switch. And so we're doing this with their proprietary technology, which is a thermochemical reactor. It's microreactors. So what we do with this, there's a little image of the system. It's an integrated, thermally efficient little block that's able to do the whole reforming process with heat recuperation and so on in this single monolithic block. So we're able to do this at low OPEX, and at the same time, because it's also highly scalable and it's a modular system that uses low cost and high throughput manufacturing methods, we can also have low capex. So with this, you have these low costs that enable you to decarbonize the process at a very advantageous dollar per ton of CO2 abated rate. And finally, the system is more than 10 times smaller in terms of physical footprint than conventional reactors. This really makes it adapted to distributed small scale applications. And so by being adapted to these small applications, well, you can think that we completely abate the need for distribution, which in itself brings a lot of CO2 emissions if you look at the whole life cycle there. And at the bottom left, if we're looking at producing hydrogen alone, so using the methane biogenic with water and electricity input, you have hydrogen and recirculation of unconverted feedstock that at the end gives you pure hydrogen with processed CO2. So we can reduce up to 40% the CO2 emissions without even considering carbon capture and storage. Now, if we're looking at producing syngas, so hydrogen with carbon monoxide, so we can recycle CO2 while producing hydrogen. And so with this feedstock that is 100% clean, we can have a net zero and even a CO2 negative process if we're storing this in these added value products that are chemicals for fabric, paints, production like methanol, for example. So that's really the end goal that we're looking at, a net zero and potentially carbon negative process. You can finally switch, Alessia. So where we're at right now, we're at a point where the system has been demonstrated at a scale of up to 2.5 kilograms of hydrogen per day produced. It's 10 of these little microreactor units that I was showing. We've shown the waste heat recuperation and reforming process and feedstock conversion rates above industry standards. So more than 90% of what we put in the reactor ends up being hydrogen or syngas. And so for our next steps, we're really looking into putting it out there in the industry. And so we're currently talking with potential industrial partners for a pilot project that will produce around 25 kilograms of hydrogen per day. And so at the same time, we'll also be looking at raising a pre-seed round and really bringing this innovation to the market and have an impact as soon as possible. So I'll be happy to take questions following this. And if anyone is interested to contact me later on, feel free to discuss hydrogen or our technology specifically. Thank you.
Dino, thank you so much. And I will remind the audience that actually we're going to take questions at the end of the presentations. Dino, just one quick sort of clarification. I think I heard you discuss the modularity, obviously, design, right? And the importance of that for small scale, small scale, basically replica, right? Of the technology. How much has that been a driver of the, if you can clarify, of the letters of interest that you are receiving from obviously very large industrial multinational companies?
Many companies are also interested by the modularity because it can enable them to decarbonize step by step. So instead of injecting a lot of capital right away, which is not necessarily a possibility for companies, well, you can have this single containerized unit that helps you decarbonize 1%, the next year 5%, 10%, and so on, rather than investing a few hundreds of millions of dollars right away. And so there is one of the big 5 companies in the steel industry, I cannot give out their name right now, that has given us a letter of intent for really using this technology for direct reduction of iron in their process. Maybe just one last LOI that we received from a really interesting application is a landfill gas site that currently produces biogas, which is burned and produces electricity that is injected back on the grid. But because of engineering constraints and the decreasing biogas production from the landfill site with time, well, you have this extra biogas that for the first few years of the project cannot be used by the turbines in the electricity generation plant. So right now you have this extra biogas from the landfill site that is simply burned because methane is more carbon intensive than CO2. Well, they're simply burning it. So we can come with a small system, and really instead of flaring that biogas, you can make a high value, added value product like hydrogen or liquid fuels, and actually make something out of it rather than just burning it for nothing.
Yeah,
so that's really two interesting
Thank you so much for that clarification. Okay, and on that note, it's now time for Professor Mortaderi from University of Newcastle. And Professor, I welcome here at this very late time in Australia for you. And I'll be happy to share screen and to make sure that our audience can follow, obviously, your remarks on the screen. Welcome.
Thank you very much for the introduction. Greeting, everyone. I'd like to very much similar to our previous presenter to start talking about the landscape in Australia in terms of renewable hydrogen. And then I specifically talk about one of our basically innovative work in this space. Next slide, please. Again, very much similar to previous speaker, the Australian government and all the organizations involved in research, they've developed a very thorough and detailed roadmap for hydrogen research, development, and demonstration in Australia. I was involved with that work actually. And there are 2 documents, each one, several hundred pages, as you can imagine. They came out in 2019. The first one is the roadmap on the left-hand side of the screen. The second one is actually a sort of mapping and matrix of what's happening at the moment in the country. And the next slide, if you go to the next slide, is an extract of this second document. And it shows the activities, whether they are completed already, whether they're in progress or proposed. At the moment, there are 23 specific hydrogen-related activities in Australia ongoing. Industry and government already spent about close to $500 million over the last few years on hydrogen. The government has spent and committed to about $10 billion over the next 5 years to essentially clean energy technologies, of which about $2 billion, as you can see on the right-hand side of the screen, has been allocated for hydrogen. Now, out of that $2 billion, the federal government, through various schemes, is contributing about $1 billion over the next 5 years. State governments in Australia, they're putting up the 500 million, and the industry is matching those state funding by another 500 million. So that's the kind of landscape. In terms of timeline, very much similar to the Canadian timeline. They want to bring hydrogen to the fruition, as soon as possible. One thing which actually sort of is a differentiator for Australia compared to other countries, especially European countries, for instance, is Australia is endowed with very high quality renewable energy resources in terms of solar energy, in terms of wind energy resources, in terms of biomass, especially around the coastal areas, geothermal energy in particular within the inside of the continent, in the middle of the continent. And then Australia is a massive, very large country. In fact, it's its own continent in a way. And those two combined means Australia would be sort of equivalent of Saudi Arabia for oil in very near future. And we can produce, hydrogen, ammonia, or any derivative of hydrogen at fairly low costs in Australia and export them. Australia has already, through the United Nations, has done some extensive study with Japan and South Korea as potential big markets for Australian hydrogen, because those countries, they need the energy, but they're not endowed with renewable energy resources. So that's where we're heading. So our goal is not necessarily to just produce hydrogen for domestic consumption, but rather for export. So therefore, we're looking at much bigger targets in terms of what we can achieve. Now, if you move to the next slide, apologies for this picture to be busy. I'll give you a background to why this particular innovation we've basically worked on over the last few years. The conventional way of producing hydrogen, as you know, is via electrolysis. And electrolysis needs water as a feedstock. Now, the quality of that water must be very high, because most of the, at least available electrolyzers, are very intolerant to salt content. So if the salt content of water is beyond a certain level, they don't work. So that combined with the fact that we don't want to compete with sort of drinking water resources, means we got to think about other ways of basically feeding electrolyzers with water. And that's where our technology comes to picture. Now, this slide here shows you that of the available economically and logistically viable water resources that can be used globally for all humankind, activities, we've already consuming 75% of it. So it's not surprised that a lot of regions around the world are under water shortage or water stress. Within a short period, by 2040, in fact, we're going to max that. And then we're going to start looking at for other resources. Anyway, so when we're talking about the big picture in terms of hydrogen production, therefore, we shouldn't think about those conventional sort of freshwater resources that are scarce for hydrogen production. We should think outside the square. So for that reason, we've been thinking about using atmospheric moisture, because if you capture the atmospheric moisture, the water that you get there is almost deionized water. There is no essentially salt in it. Therefore, you can feed it directly into an electrolyzer without the need for removing the salt or any processing. And that actually reduces the cost, because treatment of water for electrolysis units is a considerable cost of hydrogen production. So we're trying to avoid that. If you move to the next slide. With that in mind, we developed a technology with dual purpose, in fact. That technology has a commercial name, hydro harvester. It is an atmospheric moisture capture or atmospheric moisture generator. It's been designed to produce almost deionized water for energy applications, in particular hydrogen production, as well as drinking water if needed. The genesis of it goes back to a few years ago when we actually selected as one of the finalists in the Global X Prize for atmospheric water generation. And this technology has won, a lot of awards in South Australia, outside, through clever engineering and using a desiccant-based approach, essentially through an absorption and desorption approach, we can capture water from air. And interestingly, the energy footprint of this process is significantly lower than conventional ways of producing water, which are essentially based on refrigeration cycles. Typical refrigeration-based atmospheric water generators, depending on where they get their energy or electricity, the unit cost could be anywhere between $1 to about $4 per liter of water that is produced from air. Whereas our technology produces the same water from air at a cost of about 5 cents Australian. So it's significantly lower. And more importantly, for energy applications, as you can see in this slide, it has negligible salt content, less than 5 microsiemens per meter. Now, put it in perspective, the drinking water that we drink every day has about 5 microsiemens per meter in terms of salt content, in terms of electrical conductivity of the salt. And if you look at even the bigger picture, the seawater has electrical conductivity of 5 million microsiemens per meter. And you can see, because a lot of people are talking about using seawater as a feedstock for electrolyzers. Yes, that's doable, but then you got to reduce the salt content from 5 million to something less than 20. So essentially, it's a reduction in the order of 6 orders of magnitude, which is a big task. Whereas in our case with atmospheric water, there's no need for it. Anyway, so that's the technology. If you move to the next slide. As you can imagine, with anything else, it was an idea first, a lot of modeling, a lot of feasibility studies, lab work for various components. Eventually, we built a little pilot plant that you can see at the back here in the photo that I'm on with one of my postdocs. Essentially, you see a flatbed version of the hydro harvester in the front, in the right-hand side of the picture, that black box, essentially, flatbed black box, that's a hydro harvester. And the water that is generated from there is then fed to that green container where the electrolyzers are. Electrolyzers in turn are powered by those solar photovoltaic panels you can see right at the back behind the container. And then the hydrogen is produced. At the moment, we're venting oxygen out, but we're taking the hydrogen and compress it and put it into those red gas bottles. And this little plant has been designed to produce about 5 kilograms of hydrogen per day. And very recently, about a month or so ago, we actually, in front of media, we actually injected hydrogen into 2 Hyundai SUV units, SUV cars in Sydney. And the media and other people who drove those cars around the city, and that was a good PR for the technology. So where we are now, if you move to the next slide, we've just before, We've partnered with a major company in Australia called APA Group. They're owners of essentially gas pipeline assets in Australia. They have something like $23 billion worth of assets. They're very much interested in this technology because we have another component which I've not shown here, and that component is a CO2 capture unit. We can capture CO2 from air as well, hydrogen from air, we already got it, and through a Sabatier reaction, we can convert that to synthetic gas. That concept we refer to as a virtual gas well, because we're literally producing synthetic methane from air without actually drilling a hole into the ground. And that's what this company is very much interested, because then hydrogen can be transferred and stored in the form of methane and transported through their existing pipelines across the country or being exported. So anyway, for that to happen, we've gone through several more iterations, and the latest version of Hydro Harvester is what you see on the top right-hand corner, and that's the kind of pre-commercial version which we packaging, and that unit basically has 5 to 10 liters per day. It was designed for 5 to 10 liters per day water production. What else? And there is another company that we work with. They're interested in hydro harvesters just for drinking water and those sort of applications. We just signed a sort of MOU with them for manufacturing of 150,000 units. So just waiting for the legal things to happen and then move on to the next phase. And thank you very much for your time. I'm happy to answer questions at the end of the session.
Thank you so much. Thank you so much, Professor Motairi. I'm delighted now to introduce Agnes Lee from the Rocky Mountain Institute, and she's a manager in the China program based in Beijing. And Agnes, welcome. And we'll quickly share your presentation materials to guide the audience.
Sure, thank you, Elisa. I'm Agnes Lee from Rocky Mountain Institute China office. We are a think tank working on decarbonization globally. And I'm gonna introduce a little bit about China's development on green hydrogen, the policy support, and all the project developments from a broader perspective. And next slide, please. Okay, so right now, China produces 25 megaton of hydrogen per year, but about more than 90% of those hydrogen supply are based on fossil fuels, coal, bioproduct, natural gas, etc., etc. And under our estimation, the zero carbon scenario that has been done by RMI and ETC together, we estimate that the hydrogen consumption by 2050 in China would reach to about 81 million tons per year, and mostly from the heavy industry and the heavy transportation sectors. And next slide, please. Yeah, and many policies have been introduced in China on the national and local levels to support hydrogen's development. So on the national level, we have seen the National Energy Bureau and the National Development and Reform Commission, they have introduced the Energy Technology Renovation Innovation Action, which include the hydrogen industry. And also the most important national policy to support hydrogen is introduced by the Ministry of Finance to have a fuel cell vehicle demonstration and to provide reward to the qualified cities or regions to support their fuel cell vehicles demonstration for 4 years. It's basically a scoring system to support technology and development and demonstration in two fields. The first is the fuel cell vehicle, and the second is the hydrogen supply system. So all the cities or regions, if they fit criteria, then they will get a certain score. And then by the scoring system, they can get up to $100 million subsidy from the national government. And also we have seen the Ministry of Industry and Technology, they're developing a decarbonization roadmap or action plan for steel industry and chemical industries, which will definitely include the application of hydrogen in all those heavy industries. And at the local level, we have also seen on the right-hand side, there are more than 40 provinces or cities in China have introduced a hydrogen development strategy. But there's also two gaps in China's hydrogen development. The first one is, as you can see here, it's really different from the Canada and Australia cases. China's use case are mostly focused on the transportation sectors, i.e. the fuel cell. So we need to have more focus on the hydrogen development in the heavy industry field from a policy supporting perspective. And second, there's no very clear target of green hydrogen right now in China. Although we know there's a really heated discussion on green hydrogen's role in the whole energy system under China's 5-year plan, but there's really no actual national policy introduced right now. We are just still waiting for that, and also like to see how local levels would include more specific green hydrogen target in their hydrogen strategy. Yeah, and next slide, please. But in terms of the heavy industries hydrogen application development, we have seen a great wave from all those leading companies in the steel sector, chemical sectors in China. So first in the steel sector, we are seeing HBIS, the second largest steel making companies in China. They have started to construct their first direct reduced iron project with 0.6 million ton capacity per year, and they're planning to start the operation by next year. So really quick project. And we have also seen other companies like Jianlong Steel. They're developing their own technology through smelting reduction, and then partially transit from coal-based smelt reduction to hydrogen-based smelt reduction. And there's also like Baowu Steel, the largest steel-making company, is studying the feasibility of DRI, and also their companies to recycle the hydrogen from coke oven gas and then use it into the blast or in the blast furnace just to reduce the carbon emission, etc. And in the chemical sector, there's one company called Baofeng Energy Group in Western China. They have already announced their first green hydrogen project for olefin production with 100 megawatt electrolyzer capacity and 200 megawatt solar panel projects to be commissioned in later this year. And so in this way, they will just save the carbon consumption in the chemical process and instead using really green hydrogen. And also we're seeing some projects about green ammonia from green hydrogen, and also to use ammonia directly into the combustion turbine, etc. But however, China's heavy industry is still facing the challenges of first, the high cost premium, while they're facing a really intensive price competition in the domestic market. And also we are seeing a capacity issue, like how we can match the green hydrogen capacity supply with the large scale of heavy industry in China. So there's also a gap, like how we can supply really sustainable and large quantity green hydrogen to steel to steel factory, to chemical factory, etc. Yeah, and next slide, please. Okay, and also on the transportation side, transportation sectors, industry side, there's also like rapid development under the policy support from upstream to midstream and then to downstream. There's I just want to show like there are many companies are working on different technologies and in different stages right now in China, but there's also like space for China's fuel cell vehicles technology development. First, I think there are some key components such as gas diffusion layers. It's still like China does not have really mature technology, and we really depends on import. And second, there's some ancillary parts in the whole fuel cell engine system. For example, the compressor, etc., in which China are still lagging behind, and also for hydrogen storage, China is still lagging behind Europe and behind Japan, US, etc. So I think this is the progress of hydrogen development right now in China. And the next slide, please. This is what RMI is, our team is doing right now. So we are just developing a project in China to promote green hydrogen's development. It's called the China Green Hydrogen 100 Initiative. So we want to just promote this target to support the green hydrogen capacity in China to reach 100 gigawatts by 2030. And through this project, we want to build an ecosystem with policymakers, industry off-takers, the OEMs, the researchers, and global partners, just to propel policy making and technology development and pilot project demonstration about green hydrogen in China. Yeah, and I think that's all my presentation. Yeah, and
Thank you so much. Thank you so much, Agnes. Since we have less than 10 minutes to go, but we got very interesting questions coming in. Agnes, if you don't mind, I will start with you, because we are just finishing discussing, like, obviously not only the policy dialogue about how that is obviously an enabler, right, of future innovation, and in which use cases specifically for the country. Is the state of the policy dialogue, in your view, driving the opportunities for sort of more significant or clear national commitments to green hydrogen technologies, or vice versa? Is the innovation driving the need for policy alignment? Thank you.
Yeah, I think first, it's definitely the top-down approach really works. So through the top-down, through the policy discussion globally, China has committed its carbon neutrality goal. And then in that case, green hydrogen got the spotlight. This is the key, the key issue, the key solution. But afterward, I think right now we are seeing a really a bottom-up approach. So the industry would react to the national target, the national commitment, and then they will just develop all those technologies and the standards, etc. So right now we're seeing companies making targets themselves about green hydrogen capacity, and they're making standards of green hydrogen from an industry basis, and they want to just promote their concept, their standards to the national level. Yeah.
And to that point, the follow-up question was, actually, what is the role of policy in that case in lowering the cost of green hydrogen deployment? Obviously, with respect to China.
Yeah, I think in China, the policy really would support the scale up of hydrogen and then bring down its cost. So I think right now in China, the capex is relatively really low in China. So it's just a matter of scale. So how can you just further bring down the cost? And also, I think there's also we really need policy on the electricity price side, not only the hydrogen itself. We need to do something about the power system, like how to not only for just general power system reform to bring down the electricity price, but also if we can have some incentive specifically for green hydrogen production. To have some incentives to bring down the OPEX of that.
Thank you. Thank you so much, Agnes. In fact, OPEX and CAPEX are actually extremely important sort of hurdles for investors as well. And so for private-public partnerships, obviously. And we are actually having many questions coming, so I'll try to bucket them all and try to get them answered. If we're thinking about Professor Mogdaeri, how does the current total cost per kilo of the harvest water compare with the cost per kilo from the desalinated water? I think you touched on that, but if you could reiterate, that would be great.
You see, generally speaking, if you're looking at drinking water, the cost of producing drinking water from the atmospheric water generation is much higher than desalination, because you've got to contact a very large volume of air, which has on average 25 grams of water per meter cube to generate that water, whereas you want to desalinate something, you have already a body of water. So in terms of cost comparison, desalination may cost about 10 cents per meter cube, per meter cube, whereas, hydro harvester, which is the cheapest atmospheric water generator, is costing about 5 cents per liter of water. So it's significantly different. However, when it comes to production of hydrogen, the drinking water is, as I alluded to earlier, is not in terms of salt content, is not adequate for electrolyzers. So you got to reduce the salt content almost to zero. And that means additional units of, let's say, reverse osmosis from conventional desalination. And in that case, the cost exponentially goes up and becomes very expensive. So there is a point where atmospheric water generation becomes cheaper than actually desalination to produce the ionized water.
Yeah, thank you so much. And I have actually a question for both Dina and Professor Mogdaeri, actually. As innovators, which are the hurdles that you've been experiencing in implementing green hydrogen innovations at scale? Is it in the lab sort of breakthroughs, or is it instead in the real partnerships and the viability, obviously, and the access, right? To sort of the use case.
Do you want to go first, or do you want me to go first?
Well, yeah, sure. I can go really quickly at it, and you can follow up. Well, for us, of course, we're not necessarily out of the lab and at scale, but I definitely see the hurdles that are coming up. And one of the big ones is just getting the funding to put it out there, because it's an industry usually that is really risk averse, and everything has to be working perfectly day one. It's not software, right? It has to be, you can't update it online once it's out there at the client side. So you need a lot of funding to make something work day one, but you haven't never done it at that scale. There's the usual valley of death, as they call it, in this sort of startup life cycle. So for me, that's what I see personally as one big hurdle.
And Big Dad.
Yeah, I mean, I would say, just to answer your question, there's old saying, 10% inspiration, 90% perspiration. So the idea and work in the lab is the easiest part, I would say. The rest is, to get support and get it to commercialization is another thing. One thing which is actually missing from the picture is, I mean, a lot of people like us and, even policymakers, everybody, they're focusing so much on the production of hydrogen. If there is no market for hydrogen, which is the other side of the coin, then there is no future for hydrogen. So there must be some policy instruments to actually encourage companies, encourage end users to uptake hydrogen. And obviously, steel industry is an example. Shipping industry is another example. They could use ammonia, for instance. Transport is another example, but there are other industries. There must be a lot of incentives for those industries to scale up consumption of hydrogen. So to drive the other side of the equation.
Thank you. Well, thank you so much. We are actually at time. And I can't believe how the workshop went by so fast. I really appreciate you all participating, our audience for just being so active and you know, participating not only in the discussion of the breakthroughs, but also in the understanding of how, you know, policy dialogue and policy enablers are so important for such innovators to actually be able to scale their tremendous work. Thank you so much. Appreciate your participation. Thank you.